All right, welcome back to day 5 of our introductory physics class. Today, I wanted to start off with that example problem that we were doing together as like the ending of our last class. So we kind of verbally talked through what the velocity time graph and acceleration time graph would look like from this particular position time graph. But I want to show it to you so that you can visualize it as well as just hearing what it would look like. But before I show you what the graphs are, I want to make sure that we understand conceptually what is happening from this position time graph. So I have a couple of questions that I want you to think through. Jot down your answers on a piece of scrap paper if you have it handy. And this is going to be kind of our review from last week. All right, so there's that position graph in the corner. And I want you to take a couple of minutes and think through these questions. Again, jot down your answers if you have paper handy, and we will talk about the answers in a few minutes. All right, so even if that wasn't quite enough time for you to think through all of the questions, that's okay. I just wanted to give you a quick look at what some of the questions might be that relate to motion graphs like this. So let's think through. Number 1, at what times was the particle at rest? So remember, when we're looking at a position time graph like this, the particle will be at rest. We can know that when the position is not changing. So anytime that there's a horizontal line in a position time graph, that means the position was constant throughout that whole time interval. So we can see that would be from 0 to 2 seconds, from 7 to 12 seconds, from 16 to 18 seconds, and then again right at the end from 19 to 20 seconds. Those are all of the times where we have a flat or a horizontal portion of our position time graph. Number 2, when was the particle moving in a positive direction, and when was it moving in a negative direction? So it was moving in a positive direction when the slope of our line is positive, right? So that means a positive velocity, okay, positive in direction. So we can see those portions of the graph happen from 5 to 7 seconds, from 14 to 16 seconds, and then from 18 to 19 seconds. And then vice versa, negative direction would be when we have a negative slope. So that would be 2 to 5 seconds and 12 to 14 seconds. Number 3, what is the total distance traveled over that 20-second interval? Sorry, can you guys see my answers? I might not have shared that slide. Okay, hopefully you can see them now. What is the total distance traveled over the 20-second time interval? So we just add up all of the differences in the positions. So from 0 to 2, our position doesn't change, so there's 0 there. And then it goes down from 0 to -3, so that's 3 meters that it traveled. Remember, total distance doesn't care about the direction, it just cares about the magnitude, because displacement is the vector. That's the one that cares about the direction. Right, so we have 3 meters, and then it jumps from -3 way up in the top there. It's cut off on my screen, but hopefully you can still see it. And then the position doesn't change for a little while, so we don't have to add on any new position from that. Okay, then it goes down to -6. So that's a change, I think, of 8, if I remember my numbers correctly. And then it jumps from -6 to -2, which is a difference of 4. And then from -2 to 0, so that's a change of 2. So if we add up all of those changes, then we'll get our total distance traveled, which is 22 meters. Okay, I'm going to pause here because I see some questions in the chat, and I just want to make sure that I can address them. Depending on the frame of reference, negative and positive direction can be interchanged. That's true. It depends on our reference point, which is, you know, what we had talked about last week. In this case, we're just making the general assumption that up is positive and down is negative because we can see those indications on our scale there on the y-axis. Casey, I see your question, velocity is the vector. That's true, but displacement is also a vector. There are lots of different things that are vector quantities. And remember, that just means we're interested in both the size of it, the magnitude, and what direction it's going. So velocity is a vector, displacement is a vector, acceleration is a vector, force is a vector, momentum. There are lots of different things that are vectors. Vectors is just a category of quantities. Just like we have a bunch of different things that are scalars, right? Time and energy and temperature and speed and distance, all of those things. Those are all scalars because we don't care about the direction that they're going. Okay. So let's keep going on these questions then. Number 4, what is the particle's net displacement over the 20-second interval? So remember, displacement is only interested in where we start and where we end up. So we're starting at a position of 0, we're ending at a position of 0. Our total displacement, or our net displacement, is 0 meters. Because we ended up exactly the same place where we started. Number 5, what is the instantaneous velocity, magnitude, and direction of the particle at t equals 4 seconds? So I see right away that there's a typo in this answer. My apologies about that. I'll fix it before I upload it to Canvas later today. But our velocity at 4 seconds, remember, the velocity is the slope of the position time graph. So we're going to be taking the slope at 4 seconds. And so if we do our rise over run, we're rising -3 meters during that time interval that includes 4 seconds. And so, you know, we're dropping 3 meters in 3 seconds. So our slope right there at time equals 4 seconds is -1 meters per second. Or, and here's where the typo comes in, it could be 1 meter per second down or west or backwards, whatever direction we're traveling in, right? We have to include the direction there. Number 6, what is the instantaneous speed at 13 seconds? So remember the difference between speed and velocity. Speed is a scalar, velocity is a vector. Right, so velocity needs the direction, but speed does not. Speed is just the absolute value or the magnitude of the velocity. So we can again take the slope at 13 seconds, and the absolute value of that number is 4 meters per second. Even though the velocity is negative, it's going down or backwards or west or whatever you're thinking about. So our velocity is -4, but our speed is 4. It's just that magnitude. Number 7, what is the particle's instantaneous speed at t equals 16 seconds? So we're going to approach that the same way. We find the slope at that particular moment. And at that particular moment, 16 seconds, we're starting off our horizontal section of the graph. So the instantaneous speed right at that moment is 0 meters per second. Number 8, what is the average speed of the particle over the 20-second interval? So remember, average speed is the absolute value of average velocity. And for average velocity, we take the total displacement divided by the total time, which I guess ties into number 9. Sorry, I skipped ahead in my brain. Average speed is total distance divided by total time. So our total distance from part 3 was 22 meters. We know our total time interval is 20 seconds. So our average speed is 22 over 20. And you can simplify that if you want to, or you could leave it like that. And then number 9, average velocity. Remember, that's displacement over time. Our displacement from number 4 is 0. Our total time interval is 20 seconds. So our velocity average velocity is 0 meters per second. Whew, that was a lot. So on a scale of 1 to 5, 5 being I got them all right and I totally understand this, and 1 being this is like a foreign language, what is happening? How do you feel about these kinds of questions? Type it in the chat. Okay, good. I'm seeing some 5s, I'm seeing some 4s. I'm seeing a 4.75, very specific. Thank you for that, I like it. 4.8, nice, good. So it looks like we're feeling, as far as people who have responded, it looks like we're feeling pretty good about this. So that's great. There are on Canvas some practice activities that you can do. I did post all of the answer keys to those. I haven't posted the book problem answer key yet. I will try to do that later today after class is done. Just slipped my mind to do that one. But all of the other answer keys are posted there on Canvas. So check those out if you have been following along and doing those practice problems. But if you haven't, then there are still great practice problems for you to do on Canvas. Oop, sorry. Okay, so we're gonna look now at what our graphs look like. And so we had talked through these solutions, let's see, on Thursday, because we didn't meet together on Friday. So we talked through these together on Thursday. I just recreated at the top there what our position time graph looked like. I didn't include the numbers because that's a lot to try to make PowerPoint do, but that's the basic shape, right? And so when we talk through the basic shapes, remember to go from a position time graph to a velocity time graph, we're taking the slope of each section. So take a look at each section individually, and I put there dotted lines for all of the key points of interest in our position time graph. So we're going to take the slope of each section individually, and then we'll draw that into our velocity time graph, right? So if we're looking at that first section, the slope of a horizontal line is 0, so our velocity is 0. And remember, acceleration is the slope of velocity. So if our velocity is also a flat line, then our acceleration is 0. The next section, we see we have a negative slope, and using the numbers that we can see on the previous slide from the graph, that gives us a slope of, I think it's -1. So our velocity is at a constant -1, more or less, right? But that velocity time graph at that moment is a horizontal line. So our slope of our horizontal line is 0, acceleration is 0. The next section, we see we have a pretty steep positive slope, and I believe that slope is +2, if I remember correctly. Maybe it's 2.5. So we draw our velocity line at a constant 2 or 2.5, whatever it was, for that particular time interval. But you can see the velocity time graph, it's still a flat line, so our slope, our acceleration is still 0. So we draw a 0 acceleration there. Next section, we have our constant position, because it's a horizontal line. Slope of a horizontal line is 0, so velocity was 0. And that's a horizontal line, so the slope of that is also 0, right? So you break down each section individually, taking the slopes as you go. And this velocity time graph, you can see, has these kind of stepwise function look to it. But each portion of that velocity graph is a horizontal line. And so the entire time, even though we had this crazy up and down position time graph and this crazy up and down velocity time graph, the entire time our acceleration is still 0, because all of those velocity time sections are horizontal lines. Now, this graph is very idealized, right? So you can, maybe you can see And the velocity time graph, the lines connecting the green sections are like a darker blue. And they are dotted, but they're dotted on top of a dotted line, so it's a little tough to see that. But I connected them with a dotted line just to show that we don't really know what's happening during that time, that like instantaneous time interval. Because of course something can't change directions instantly, like nobody's that good. So there is going to be some degree of, acceleration and deceleration, if you will, as those jumps are happening. But we don't know what those are, and we don't see them indicated in the position time graph. So we're just going to say this is an ideal case, and we're ignoring our brief speed up and slow down portions. But of course, that's not actually realistic. Okay, any questions, comments, concerns about this example? Okay, makes a lot more sense now. That's good. I'm glad. You didn't see graphs like this in school as step graphs. They were curved, so it was a little bit different. Yeah, every teacher does it slightly differently. I just think step graphs are the easiest to visualize, maybe. But there will be cases, and we might have some cases that we do together, where the position graph is a curve instead of like straight lines. And so that will affect the shape of our velocity graph and then our acceleration graph as well. Okay, a comment about still being confused going from position to velocity and velocity to acceleration. Yeah, so that's just a matter of getting comfortable taking the slope of a line, which is a skill that you probably learned in Algebra 1 in middle school, high school, whenever you ended up taking that class. So just get practice at thinking about, is the slope positive or negative or flat, first of all. If you can visualize that, then you have a really good head start as to thinking about how to make, like what is happening with your velocity, right? If we have a positive slope on our position graph, then we have a positive velocity. And same idea going from velocity to acceleration. We're just looking at the slope of the line at each section. So if we have a positive slope versus a negative slope versus a flat line, that tells us about the acceleration, right? If we have a positive velocity slope, then we have a positive acceleration. If we have a negative velocity slope, then we have a negative acceleration. So if you're still confused about this, I definitely recommend that you check out some of those resources that I posted on Canvas, and the solutions are right there for you as well, so you can check your work as you're doing it. Right, also remember that going from one to the next is the derivative, right? That is correct, Haley. If you know how to take derivatives, if you've taken calculus before, then that's another way to look at this, a mathematical way. And we're gonna go more into detail about that today. So even if you don't know how to take the derivative, hopefully you'll learn how to do that today. Any other questions, comments, concerns before we move on? Okay, if at any point there are, just let me know, and I'll answer any questions as best I can. All right. So, like you were just saying, we can find these velocities and accelerations graphically, like we were just doing, taking the slope of each line section, or we can do it mathematically using calculus. So, calculusly, if you want to invent words like I do. So, graphically, like I said, we are going to look at slopes. And today I'm going to teach you what I mean by areas under the curve. But according to calculus, what we're actually doing is taking a derivative and taking an integral. So those ideas, area under a curve and integral, are new for this class. You may have seen them before if you took calculus in high school. But even if you didn't, hopefully by the end of today, you'll get a little introduction to those things. Okay, so derivatives mathematically. Here's where we're going to transition from looking at graphs to thinking about equations. Okay, so when you're taking derivatives, and this is all Calculus 1 stuff that we're going to be talking about. So, if you're signed up to take Calc 1 in the fall, then this is stuff that you'll see again at college when you take Calc 1. But I want to give you a brief introduction to it. It's okay if it doesn't make sense the first time you see it. It didn't make sense for me either the first 2 times I saw it. But I want to introduce it to you so that you, have a head start, I guess. So when we're taking derivatives or, taking slopes of lines, there are a couple of different rules that we're going to be following. And we'll go through some of those rules today. There are more rules than the ones that we're going to go through. But again, that's what your Calc 1 class is going to be for. And I don't want to steal your professor's thunder totally. So we'll just go through a couple of the key ones that you might want for Physics 1. Excuse me. So to start off, we have the power rule. So when we're taking the derivative of a function, and we want to apply the power rule, here's what we do. We multiply the coefficient, the number out in front, by the exponent, and then we subtract 1 from the exponent. So here's what I mean by that. Okay, and I'm going to show you all kinds of different notation for derivative that you might see. So they'll look a little bit different each time. That's intentional. But when you see d over dt, that means we're taking the derivative of something, of a function, and that bottom variable d something, in this case dt, that tells you which variable we're going to be taking the derivative with respect to. So if our function is t to the 5th, time to the 5th power, when we take the derivative of this function, t to the 5th power, we're going to multiply the coefficient by the exponent. So in this case, the coefficient, the number in front of the t, is just kind of an assumed 1. Right? We don't actually have to write 1 t to the 5th, but that's the same thing as saying t to the 5th. So we multiply that coefficient by the exponent, in this case 5 times 1, and then we subtract 1 from the exponent. So t to the 5 minus 1. So the derivative of this function, t to the 5th, is 5 t to the 4th. Right, you can see we've brought that exponent down, multiplied it by the coefficient in front, and then subtracted 1 from the exponent. So if we were to graph the function t to the 5th and take the slope of that, all of those tangent lines together, then we would end up with a graph that looks like 5 t to the 4th. That's what we're doing mathematically. Here's another example. D over dx of the function 3x squared. So this time you can see we have dx in the bottom, not dt. So we're going to be taking the derivative with respect to x, not t. You can see there's no t anywhere in that line. So we're just going to be focusing on the variable x now. Okay, so again, we're going to multiply the coefficient, in this case 3, by the exponent 2. So 3 times 2. And then we subtract 1 from the exponent. So squared minus 1. That gives us 6x to the 1, or just 6x. So the derivative of the function 3x squared is 6x. Right? If we were to graph the function 3x squared and take the slope at each point, it would create a graph of the function 6x. Here's another example. The derivative of 15. Well, you can tell from the very beginning, d over dt, that we're supposed to be taking the derivative with respect to time, that variable t. But there's no t anywhere in that function. It's just 15. So that's kind of like saying 15 times t to the 0. T doesn't exist in that function. So, following still the power rule, if we bring that exponent 0 and multiply it by the coefficient, 15, then it's just 0 times 15, which is 0. So anytime you have a constant number, the derivative of a constant is 0, right? And you can think about that graphically too. Like if we have a constant position of 15, and we want to take the slope of that line, well, if you have a constant position of 15, that part of the graph is a horizontal line. And the slope of a horizontal line is 0. Right? Same idea here with derivatives. It's just mathically, calculusly, instead of graphically. Okay. So like I had already pointed out in the examples above, you can take the derivative of different variables, and that initial fraction tells you which variable that you're interested in. Any other variables that you might see, you can just imagine are constants. So for example, if we have this function, x t to the fourth, and we want to take the derivative with respect to t, right, d over dt, then we're just going to imagine that that x out in front is a constant. And so we multiply our coefficient by the exponent. Coefficient is x in this case, so 4 times x. And then we subtract 1 from the exponent, so 4 minus 1. Our derivative with respect to time is 4xt cubed. Okay. So I'm gonna pause my screen share right now and take a look at your chat. If you have questions about this power rule, please type them into the chat so I can address them for you guys. All the integrals, we'll get there kind of. On the acceleration, on the drawing, once you have the slope, why do you need to do the calculus? Because you won't always know how to draw the function that is given to you. Like I don't know how to draw off the top of my head xt to the fourth because I don't know what x is. So if I don't know how to draw the function, then I can't take the slope of the drawing that I can't do. But I can still calculate what it's supposed to be using the calculus, using the derivatives. So even if you can't draw it, or if you don't have time to draw it, then you can use derivatives. You can use this calculus. Okay. Vincent, so the d over dt and d over dx is just a notation in front of the derivative. That notation is telling you to take the derivative. D over d something means find the derivative of. But there are other ways to write out, take the derivative of as well. And I think I have some different examples of like different notation coming up on the next slide. And I'll point that out too. But that's one, well, I guess 2 different ways to write it to tell you what to do. Will you have any tries for derivatives? Yes, you will. I have a couple give it a tries in just a couple minutes. It's like when the division sign tells you to divide, or the plus to sum, etc. Yeah, it's exactly like that, right? It's just the symbol that we use to tell you what to do. Math is very bossy, right? It tells you what it wants you to do all the time. So d over d something tells you to take the derivative. And Colby, you like to think of it as the d stands for delta, which means change. So change in blah over change in blah blah, which is slope or derivative. Absolutely, that's exactly right. The d basically stands for delta, that triangle symbol that we talked about last week, which means change in something. And the derivative is a change in something over change in time, or how the rate of something changing relates to something else. And that's a derivative. Absolutely. Okay. So continuing on. There are a couple of other rules that are going to be helpful for you. And over here in this blue box in the corner, this is another different notation that you might see for derivatives. So if y is our function, like y equals mx plus b, that's a function that you've hopefully seen before in Algebra 1. If you want to take the derivative of the function y, we would call it y apostrophe. And that apostrophe we just call prime. So y prime means find the derivative of the function y. That's another notation that you might see. Okay, so we have the power rule where we take the exponent down and then subtract 1 from the exponent. Here's the sum rule. The derivative of the function f plus the function g equals the derivative of f plus the derivative of g. Okay, so these could be any two functions. F and g just stand for some function, whatever it is, x squared or x cubed or 5t or whatever the function is. It doesn't matter. If you're adding two functions together and you want to find the derivative of those things added together, you just find each derivative and then add them together. So for example, right, if our function y equals x squared plus x cubed, we can find the derivative of y with respect to x, dy dx. And so we're going to apply the power rule here. So we multiply the coefficient by the exponent, subtract 1 from the exponent. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. So the derivative of our whole function, y, is those two pieces added together, 2x plus 3x squared. A very similar rule is the difference rule. The only difference is we're taking the difference. Instead of adding them together, we're subtracting them. So the derivative of f minus g is the derivative of each piece subtracted from each other. So for example, here's a totally obscure variable v, right? So if we want to take the derivative of that function with respect to v, d over dv, and our function is v cubed minus v to the fourth, then we take the derivative of each piece and we subtract them, right? 3v squared minus 4v cubed. Okay, and again, that's applying that power rule that we went through on the previous slide. And for things called higher order derivatives, we can take the derivative of a derivative of a derivative of a derivative as many times as necessary. And I mean, once you get to a certain point, it kind of becomes silly to keep taking a derivative. But you can do it as many times as you need to. So for example, if our function f of x, that's another way to write a function. If our function is 5x cubed minus 3x squared plus 10x minus 5, a long function, and we want to find the derivative of that function. So you can see there's that prime notation. F prime x means the first derivative of that function f of x. And so we apply that power rule, right? We multiply the coefficient by the exponent. So 5 times 3 is 15. Subtract 1 from the exponent. So 15x squared is that first derivative of 5x cubed. We do the same process for the rest of it. Negative 3 times 2 is negative 6. So our next piece is negative 6x. The next piece, 10x, is like saying 10x to the 1. So bring down the 1. And then x to the 0 is 1. So that chunk, the derivative of it is 10. And if you remember from previously, the derivative of any constant number is 0 because the slope of a constant graph is 0. So that's called the first derivative because we've directly taken the derivative of the function. Now you can do that again and find the second derivative by taking the derivative of the derivative. And in that case, we just add on another prime in our notation. So f double prime or f prime prime is the derivative of our derivative. So again, we apply that power rule just like we saw. 15x squared, the derivative is 30x. The derivative of 6x is 6, so 30x minus 6 is our second derivative of that function. We can go even more, take the third derivative, x triple prime, and that's the derivative of the second derivative, which is the derivative of the first derivative, right? So it's just this whole chain of things. And the derivative of 30x is 30. That 6 is a constant, so it'll go away when we take the derivative. At some point, it just becomes really tedious to write all of the apostrophes next to it. So once we reach the fourth derivative, we just write 4 in parentheses and know that we're talking about a derivative. But that's the derivative of the third derivative, which is a constant number, so our derivative of that is 0. Okay, why does that matter? Why do we care about the higher order derivatives? Well, that's because if you remember, our position, velocity, and acceleration graphs are all related to each other through their slopes, right? And so to get to the velocity graph, we take the slope of position. And to get to the acceleration graph, we take the slope of velocity. Well, that means that we've taken, for our acceleration graph, we've taken the derivative of a derivative. So acceleration is the second derivative of position, right? Because we took the slope of a slope. So that's why we care about a second derivative. We won't really use a third derivative or fourth derivative, although we did last week go through that like series of terminology. So you have position, velocity, acceleration, jerk, snap, crackle, pop, right? Those are all of the names of the different derivatives. So in this case, you can see on the screen, they're called first derivative, second derivative, third derivative, fourth derivative. When we're talking about position, position would be our function, velocity is the first derivative, acceleration is the second derivative, jerk is the third derivative, snap is the fourth derivative, crackle would be the fifth, and pop would be the sixth derivative. Okay. Let me go ahead and check the chat, see if you have any questions, comments, concerns. Is there any specific point we're aiming for? It depends on what you're asked, right? So if you have a position and you're asked to find the acceleration, then you would take the second derivative. You'd find velocity first and then take the derivative of that to get acceleration. It would tell you what you're aiming for. What would graphically mean the second or third derivative, right? So that would be second derivative of position is acceleration. If we had an acceleration graph that was not just 0, which I think we had an example of that last week, and it was at like a constant negative 9.8. If we took the slope of our acceleration graph to find the jerk or how our acceleration is changing over time, that would be our third derivative. So Gabriel, hopefully that answers your question about what would graphically mean second or third derivative. Each derivative has its own purpose. Yes, absolutely, Joshua, that's true. And you said first derivative is slope, second is maximum and minimum. That's another good way to look at it. I won't go into that right now, but if you've taken calculus and you already know that, that's absolutely correct. Third derivative is rate of change. Any derivative is a rate of change. It's just what are you looking, the rate of change of what is what we're interested in, right? So our first derivative, again, thinking about things that we've already talked about, position, velocity, acceleration. Our first derivative is rate of change of position. Our second derivative would be like the rate of change of velocity, how our velocity is changing over time. Our third derivative would be how our acceleration is changing over time, the rate of change of acceleration. Okay. In mathematics, you don't use greater than 3. But in physics, greater than 3 usually corresponds to a certain physics term. That's right. Yeah, I mean, you might have to prove that you can do it in your calculus classes, but really for us, for this class, we won't need to go past acceleration. So that would be our second derivative. Okay, I don't understand what happened to 10x plus 5 in the higher order example. Okay, so anytime we have a constant, so like without the x term attached to it, any constant number is going to disappear when we take the derivative. Because again, if we were to graph it and we have a constant position, the slope of a horizontal line is 0. So you could, at the end of our first derivative, you could write 15x squared minus 6x plus 10 minus 0 if you wanted to. But that wouldn't change your answer at all. That minus 0 at the end would not change your answer whatsoever. And you can see in that first derivative then, we're left with a constant plus 10 at the end. Well, since that's a constant, when we take the derivative of a constant, it's 0. So our second derivative could read 30x minus 6 plus 0 minus 0. But again, those zeros at the end don't change our final answer. Joshua, you say also 10 to the 1 minus 1. Anything raised to the 0th power is 0. Anything raised to the 0th power is 1. Right, so 10x in our function, if we apply that power rule, you know, we can imagine that 1 is the exponent of x, so 10x to the 1. Right, we multiply our coefficient 10 by that power 1, and then we subtract 1 from that exponent. So it becomes 10 times x to the 0. Anything to the 0 is 1. So 10 times 1, which is 10. Right, that doesn't change your constant. So that's how we got it from 10x to a constant. Hopefully that makes sense. Do you guys have any other questions about that, about this slide, the sum rule, the difference rule, or the higher order derivatives before I move to the next slide? Okay, great, Marco, that answered your question. Awesome. Okay. So I think, if I remember correctly, I think the next slide is, give it a try. Yes, okay, give it a try. So we're gonna apply those couple rules that we have just talked about: the power rule, the sum rule, the difference rule, and the higher order rule. And I want you to take just a moment, I'll pause the recording to give you some time, find the derivatives of those functions. And once you have them finished, go ahead and give me a done or a ready in the chat. All right, let's take a look at our answers. Okay, so for part A, we're taking the derivative with respect to x. So again, we're going to apply that power rule, bring the exponent down and multiply it by the coefficient, and then subtract 1 from the exponent. So the derivative of 12x to the 4th is 48x cubed. The first derivative of our function y, 6x plus 1, is 6. Remember, 1 is a constant, so when we take the derivative, it'll go to 0. And our x, the exponent on the x, will turn into a 0, which means it'd be 6 times 1, which is 6. And then the first and second derivative of that function x, this is like a real life example. So remember, x stands for position. So when you take the first derivative of position, that's velocity. So this would ask you to find the velocity of that position function. The 2 out in front is a constant, it'll go away. So we're left with the derivative of negative 4t, which is negative 4. And then that last chunk, minus 4.9t squared. That squared comes down, multiplies by 4.9. So 2 times 4.9, t to the 1, which gives us our velocity of negative 4 minus 9.8t. Our second derivative, this is how you would notate second derivative. In the previous slide, we saw you just add another apostrophe, another prime. This is another way to write it. d2x over dt squared is telling you to take the second derivative with respect to time again, which gives us our acceleration, right? The rate of change of velocity with time is acceleration. That would be negative 9.8. I take the derivative of that velocity function. Okay. So there are some other rules about derivatives that I just want to introduce to you, even though we probably won't use them in this class. And you probably won't need them in Physics 1, depending on your professor, depending on if they've changed the class since I took it. But I don't think I had to use these in Physics 1. I did have to use them in Physics 2, though. And again, you'll learn these in more detail in Calculus 1. But I just want to introduce them to you so that you know they exist. The product rule, if we're multiplying two functions by each other, so f times g, we do the function f times the derivative of g plus the derivative of f times the function g. So for example, if this is our function, 6x cubed times 7x to the fourth, the derivative of this, we would take, so I'm calling the function f to be 6x cubed, and g is 7x to the fourth, right? So we bring f down, 6x cubed. We take the derivative of g, so d dx, 7x to the fourth, plus our function g, 7x to the fourth, times the derivative of f, so d dx, 6x cubed. And we apply the power rule again, so 6x cubed times 28x cubed plus 7x to the fourth times 18x squared. And then we can multiply those things together and get our final answer, which is 294x to the sixth. Now, in this case, there are multiple ways to go about doing this example. This is just the method that I chose because it highlights some of those other rules that we've already talked about. But if you think of another way to do this example, you're more than welcome to try it that other way too. And then the quotient rule, if we're dividing our functions, so the derivative of something divided by something else. And that's g times the derivative of f minus f times the derivative of g over g squared. And so I guess a kind of catchy way to remember that is low d high minus high d low over the line and square the low. And that d, like low d high, means the derivative of that top function, the high function. So low d high minus high d low over the line and square the low. Okay. So, for example, if our function is 4 over x to the sixth, we want to take the derivative of that. Then we do low x to the sixth d high, the derivative of a constant is 0, minus high 4, d low, the derivative of x to the sixth is 6x to the fifth, over the line and square the low. So divided by x to the sixth squared, which would give you negative 24x to the fifth over x to the 12th. That can simplify to negative 24 over x to the 7th. Now, can you guys see the alternate way to do this particular example? If you see it, go ahead and type it into the chat. How else could we do this example? Your math teacher would sing the low D high thing like a cowboy. Man, I wish you could demonstrate that for us. That sounds fantastic. You use these rules in calculus, and yeah, these are the standard rules. Absolutely, and you'll see them again in Calc 1 at FIT if you take Calc 1 at FIT. All right, so the alternate way, I don't think I typed this out, but the alternate way to do this quotient rule example would be to recognize that anytime you have an exponent in the denominator of a fraction, you can bring it up and make the exponent negative, right? So the function 4 over x to the 6th could also be written as 4x to the negative 6. I mean, it's the same thing. But then we're not dealing with this gross fraction, so we don't need to apply the quotient rule. We could apply the power rule. So we would just take our exponent and multiply it by the coefficient. So exponent is negative 6 times our coefficient 4. So negative 6 times 4 is negative 24. And then we subtract 1 from our exponent. Now remember, negative 6 minus 1 is not negative 5. Negative 6 minus 1 is negative 7. So our answer then would be negative 24x to the negative 7th, or negative 24 divided by x to the 7th. They mean the same thing. So I would say if you feel more comfortable doing the power rule than the quotient rule, keep an eye out for those sorts of situations where you can just turn your fraction into a not fraction and then apply whatever rule is easier for you to do. I just wanted you to see what these two rules look like, but again, we won't really be doing them, at least as far as I know right now. We won't need them. You were always given these rules in AP Calc classes. Is that the same in college calc? My memory says no, you will need to remember them. Your professor will teach them to you, but on a test, you would need to remember them. But that could depend on your professor again. I just always had to memorize them for the tests. RIP formula sheets. Big sad. I know. Some professors allow you to do formula sheets for some things. And by formula sheets, I mean like a little 3x5 index card with whatever formulas you need. You might be able to use them on tests, but not on quizzes. You might not be able to use them at all, or you might be able to use them on everything. Again, it depends on your particular professor. Yeah, time to memorize them again. That's my recommendation, so that you don't have to waste time looking at a formula sheet too. Yeah, learn to work without it. Okay, great. So I mentioned at the beginning of class this idea of area under a curve, which is basically, I mean, it's also calculus. It's also called an integral. But we should know by now that position time graphs can give us information about velocity, and velocity time graphs can give us information about acceleration, right? We've mentioned those things. But what we also need to remember, if position time graphs can give us information about velocity, then velocity time graphs should be able to give us information about position. Same thing for velocity and acceleration. And the relationship goes both ways, right? Any good relationship is a two-way relationship. So, we've talked so far about going down our stack of graphs, so from position to velocity or from velocity to acceleration. And to do that, we take the slopes of the lines or taking the derivatives. We can also go up our stack of graphs. So we can start at acceleration and learn about velocity. Or we can start at velocity and learn about position. And when we go up the stack of graphs, that's called an antiderivative, because we're going, like, derivatives go down, antiderivatives go up. or an integral. But if, graphically, if it makes more sense to you to think of slopes instead of the word derivative, then graphically it might make more sense to you to think of the area under the curve instead of this fancy word integral. So here we have our position time, velocity time, and acceleration time graphs. So you can see our position time graph gives us this nice like bell curve looking thing. And so if we think about the slopes of our lines, we're starting off with a zero slope, which gets positive, and then smaller until zero, and then comes back down negative, and then flattens out again to zero. So that's what our velocity graph does, right? It's positive, and then it's a constant positive number for a little while, and then it decreases to zero right at 15 seconds, and then it's a negative slope, which gets a less and less negative as the position curve flattens out until it's zero again. And then acceleration, we take the slopes of each section in our velocity graph, and you can see what that does to our acceleration. But we can also, if we just take a look at the units of our graph, and this is why it's so important to know your units. We know the slope of a graph is the change in our y variable over the change in our x variable. So in this case, the change in position over change in time. Then the units would be change in x in meters, x is measured in meters, over change in time, which is measured in seconds. So that'd be meters over seconds, which gives us velocity. So thinking about this idea of how can we look at a velocity time graph and know about the position? If we look at that pink shaded area, it's called the area under the curve. And if we look at that area, well, the area of a triangle, for example, that first little section is 1/2 base times height. That's just an area formula that you'll need to know. Rectangle next to it, the area of a rectangle is base times height. Looking at those units, the base units is seconds times the height units, which is meters per second. So seconds times meters per second gives us meters. So that area, that pink shaded area in the velocity time curve gives us the displacement. And we need to be careful to remember that it's giving us the displacement, not the distance, because velocity is telling us the direction as well, right? You have a chunk of that velocity graph that's above the y-axis, and you have a chunk that's below the y-axis. So in this case, in physics, it's totally possible to have a negative area under the curve if that area is below the x-axis. Okay. And we can think about it the same way too with acceleration and velocity. If we look at the units of our acceleration graph, you can see all of those shapes are rectangles. So base, seconds times height, meters per second squared. That will give us seconds times meters per second squared, or meters per second. That tells us about the velocity. So when we're taking integrals or antiderivatives or area under the curve, it's just the opposite process as for derivatives. And really though, that's where I'm going to leave it as far as calculusly goes, because this is Calc 2. You learn about integrals in Calc 2, not Calc 1. So you'll be learning about this in Physics 2, not really Physics 1. So I'm not going to go into calculus details about it, but I'll go into the graphical details about it just so you have a conceptual understanding. Okay. So the integral calculates the area under the curve of the graph. And I put that in quotations because that word under is a little bit misleading. And you can see that in the previous slide. Under more refers to the area between the curve and the x-axis. So going back, look at the velocity graph. Right, it's a little bit misleading to say the area under the curve from 15 seconds until 27 seconds because the shaded region is above the curve, right? So really when we say the area under the curve, we mean the area between our function line and the x-axis. Okay, hopefully that makes a little bit more sense. So the formulas that you'll want to know for areas are the area of a rectangle or a square, and that's just base times height. And then the area of a triangle is 1/2 base times height. Okay. So you can see there in that green box in the corner, when you're going from graph to graph. So when you're going down the stack of graphs, we take the derivatives. So the derivative of position is velocity, derivative of velocity is acceleration. When we're going up the stack of graphs, that fancy like S symbol means integral, because integral is a fancy way to say sum. So that's S comes in. So the integral of acceleration with respect to time gives us our change in velocity. And the integral of velocity with respect to time gives us our change in position or our displacement. Okay. So an example of how to take these areas under a curve. And again, I have there in that blue box at the top, just a reminder, we can't find the position, just the change in position, just the displacement. So if you want to find the change in the position after 5 seconds, and then after 10 seconds, and then after 15 seconds, here's what we do. Okay, so we can see from 0 to 5 seconds, the area under the curve, in this case, kind of creates this, this square. And so the area of a square is base times height. Our base goes from 0 to 5 seconds, so that's 5 seconds long. And the height goes from 0 to 5 meters per second, so that's 5 meters per second tall, which is a weird way to say it, but you know what I mean, hopefully. So 5 seconds times 5 meters per second gives us an area in that section of 25 meters. So that's our displacement during that time interval. If we want to know from 0 to 10 seconds, well, we can see from 5 to 10 seconds, we're adding on this, like, I can't shape, this triangle section. And the area of a triangle is 1/2 base times height. So for that triangle, our base goes from 5 to 10 seconds. So the triangle is 5 seconds long, and it's 5 meters per second tall. So that's 1/2 of 25, which is 12.5 meters. So if we're looking at that whole time interval of 0 to 10 seconds, we add together the area of the square plus the area of that triangle, and that gives us 37.5 meters as our displacement. If we add on that last section from 10 to 15 seconds, it's a rectangle where the base is 5 seconds long, but it's 0 meters per second tall. And so the area of that section, area under the curve, is 0. There is no under the curve. There's no space between our curve and the x-axis. So that means our total displacement over the whole time interval is the square, the green square, plus the blue triangle, plus the 0 displacement, or 37.5 meters. Okay, any questions about this example so far? Okay. Got a nope. All right. So if you followed along with me in this example, congratulations, you've done more calculus. You've done integrals. I mean, sort of, right? Just like by taking the slope, you've sort of done a derivative. When you see this again later in calculus, They'll teach you how to actually write it mathematically. But this is the idea of what an integral is. It's finding the area between your curve and your x-axis. And of course that gets more complicated if your graph is not nice straight lines. Like if we can't just break it down into squares and triangles and rectangles, then it's a little bit harder, because like if you have to find the area of like an actual curve, then it's a little bit more difficult, and that's where the actual calculus would come into play. But again, that's not something that I'm going to teach you right now, because you'll learn that in Calc 2. So again, keep in mind, if the curve, no matter what, if it's a curve or straight lines or diagonal lines, whatever, we still call it a curve, the shape of our function. So if the curve is beneath the x-axis, your heights can be negative. They will be negative. So it's totally okay to have a negative area. And you'll need to keep the signs with the areas. Because if you have a positive area on top and a negative area on bottom, when you add them together, those signs are important, right? If you have 5 plus 2 versus 5 plus negative 2, you get different answers. 5 plus 2 is 7. 5 plus negative 2 is 3. So you need to keep those negative areas as negative when you're adding them together to get your total displacement. So here's another one. I want you to give this a try, and this is going to be where we end today. So before you leave, I want you to give this example a try. What is the total displacement of the object over 18 seconds? So figure out, calculate those areas under the curve, and I'll give you a minute to do that. Find the total displacement, and we'll come back and go through that solution in just a minute.